Welcome to the Semantic Kernel course, where you will discover how this powerful tool can transform the way you develop intelligent applications. The arrival of new technologies not only amazes us, but also completely redefines how we live and work. Today, we stand on the brink of another revolutionary era driven by artificial intelligence, where chips, algorithms, and innovative systems are transforming industries around the globe. One of these revolutionary technologies is ChatGPT. It has changed the landscape of interaction with AI, revolutionizing markets and redefining how we engage with intelligent systems. ChatGPT laid the groundwork for a new wave of applications that seamlessly integrate AI into everyday processes. Achieving 1 million users in just 5 days underscores the immense impact of this technology. The rapid adoption of ChatGPT demonstrates a clear demand for intuitive and effective AI solutions. Most notably, OpenAI, the company behind the GPT models, made its API available to everyone. This decision empowers developers like you to integrate these powerful models into your own applications, opening the door to countless innovative opportunities. Over time, individuals and organizations have created a variety of projects that leverage these models. These projects enhance daily workflows and productivity, allowing both individuals and businesses to improve their processes through AI integration. One noteworthy project comes from Microsoft, Semantic Kernel. The term semantic highlights its ability to work with a semantic understanding of words and data, providing contextual comprehension based on meanings. This marks a step forward in how we interact with and obtain information from AI. Kernel refers to the central framework that orchestrates components such as AI models, plugins, and external services. This modular framework simplifies integration and coordination among these elements, providing an extensible foundation for building AI-driven applications. Semantic Kernel achieves this through an open-source SDK that allows you to leverage leading LLMs like OpenAI, Azure OpenAI, and Hugging Face. This integration capability ensures that you can access the best available tools to build sophisticated AI solutions. Moreover, Semantic Kernel supports popular programming languages such as C#, Python, and Java. This flexibility enables developers from diverse backgrounds to easily adapt and integrate the framework into their existing technologies. With Semantic Kernel, you can build intelligent applications with remarkable capabilities. The potential is immense, and the applications are as diverse as your imagination. For example, you can develop solutions that process and understand natural language. This capability allows applications to interact with users in human-like and meaningful ways. Another powerful use case is the dynamic and personalized generation of content. From drafting emails to creating marketing materials, Semantic Kernel allows you to tailor content to the individual needs of users at scale. Semantic Kernel also excels at integrating language models with business tools and data. This integration can enhance business processes and provide actionable insights by combining AI capabilities with existing infrastructure. One of the most exciting possibilities is the automation of complex workflows that combine AI with programmatic logic. This functionality simplifies operations, reduces manual effort, and enhances overall efficiency. Get ready to unlock your creativity and innovate like never before. Semantic Kernel provides the tools, flexibility, and scalability to bring your ideas to life. Let's dive deeper and see what you can achieve. The journey is just beginning. Once we have seen an overview of what Semantic Kernel is, let's explore the fundamental concepts of this SDK. First, Semantic Kernel has an AI orchestration layer that enables the seamless integration of AI models and plugins. This layer is responsible for combining these components to create innovative interactions with users. Similarly, the SDK offers a set of connectors that allow developers to integrate language models, or LLMs, into their existing applications. We can view these connectors as a bridge between the application code and the AI models. The Semantic Kernel SDK operates through plugins, which form the core of the AI application. These plugins consist of prompts that the AI model must respond to and functions that can perform specialized tasks. As a developer, you can use existing plugins or create your own. It's important to understand some of the benefits and use cases you can leverage by using Semantic Kernel. For example, with the advanced capabilities of Semantic Kernel, repetitive tasks can be automated, which would reduce time and human errors, allowing employees to focus better on the tasks that truly matter. Similarly, the potential of Semantic Kernel can be harnessed to analyze and interpret data to provide relevant and actionable insights in real time. By transforming data into meaningful intelligence, employees can make better decisions more quickly. Thanks to Semantic Kernel, it is also possible to improve the efficiency and productivity of individuals by seamlessly integrating artificial intelligence into their daily workflows. By simplifying complex processes, automating repetitive tasks, and delivering key information when it is most needed, employees can be empowered to work smarter, not harder. The result is more agile, focused, and prepared teams ready to achieve their goals with unprecedented speed and accuracy. For customers, it is possible to create copilots that help them optimize their processes through automation of repetitive tasks and simplification of complex workflows. This translates into less time wasted and more focus on what truly matters. It is also possible to program agents to perform tasks like organizing schedules and analyzing large amounts of data in just a few seconds. With the use of agents, unique experiences can also be created for users through advanced artificial intelligence, generating personalized recommendations based on individual behavior, preferences, and needs. Finally, we know that the world does not stop. That is why copilots are available 24/7, always ready to assist, from answering frequently asked questions to resolving tickets in real time. The possibilities with Semantic Kernel are virtually limitless. Do you need predictive analytics, multilingual support, or perhaps advanced integrations with your favorite tools? With Semantic Kernel, you can do all this and much more. Let's see how in the upcoming modules. It's time to roll up our sleeves and start creating a project using Visual Studio 2022 to integrate it with Semantic Kernel. How do we do this? Well, the first thing you need to know is that you must have Visual Studio 2022 installed. There are many online tutorials to guide you on how to install it. Once you have it installed, you will need to go to the section for creating a new project and we will select the first project template called Cancel App, which is essentially an application that allows us to run a command line to execute .NET on Windows, Linux, and macOS. So let's select this template, click on Next, and change the name to, for example, I'll make the screen smaller, Semantic Kernel Installation. We'll assign this name as part of the project name. We'll leave the other data as it is. We click on Next. In this second section, I will leave the latest framework currently available in .NET selected, which is version 9. I will leave everything else as it is and click on Create to initiate the process of creating this new project. Okay, here we have the project ready. Once it is ready, we can see that in the project section in the Solution Explorer, we have the file program.cs. What we will do is right-click on the project name. That is, on this green icon that you can see here, we right-click. We will indicate that we want to manage NuGet packages. Why do we do this? Because we want to carry out the installation of the NuGet package for Semantic Kernel. We will go to the section that says Browse and type Semantic Kernel here. I position the cursor over this line and we see that the search yields many results. We will review some of the packages that appear here throughout the course. However, the package we are interested in right now is the one that says Microsoft.Semantic Kernel. Once we have located this package, we will simply click on the Install button to proceed with the installation. We apply the changes, accept the relevant licenses, and wait for the package installation to complete. You can see that it has been installed when this icon with a check mark appears, indicating that everything went smoothly. Once we have installed Semantic Kernel, we can go to the program.cs file, clear its content, and begin by creating an instance of the kernel, which we will explore in more detail in the next video. It must be kernel with a capital K, so kernel. If you see a red mark beneath it, it means we need to import the missing namespace. Once we import it, you will see that the errors disappeared. Next, we will use the createBuilder method, and finally, we will invoke the build method. Once we have done this, basically it allows us to build a new instance of a kernel. We will see more about kernel later, as I mentioned earlier. Finally, we will indicate cancel.writeLine, and within these quotes, Semantic Kernels is running, for example, using this suggestion provided by Copilot. We will save the changes. We start running the application, and this is just to ensure that Semantic Kernel is working without any issues. It is a very simple app, but it allows you to begin understanding the Semantic Kernel environment. We will be doing more complex examples as the lesson progresses, so let's keep learning. In this section, you will discover everything you need to know about the kernel in Semantic Kernel, its importance, and how it interacts with other components to enhance the capabilities of your AI-based application. The kernel is the heart of Semantic Kernel. You can think of it as a dependency injection container that manages all the necessary services and plugins required to run your application. By providing these services and plugins, the kernel can use them as the AI requires. This is extremely practical for developers, as it centralizes configuration and monitoring of the AI agents in one place. For example, when invoking a prompt through the kernel, it will first choose the most suitable AI service to carry out the execution. Next, the prompt will be constructed using a prompt template, a concept we will explore further in the course. The final prompt will be returned to the AI service, which will use a language model or LLM to generate the requested response. The generated response will then be returned to the kernel, where it will be processed and prepared for delivery. Finally, the result will be returned to your application, ready to be displayed to users. Throughout this process, you can implement events and middleware that are activated at each step. This will allow you to perform actions such as detailed logging, providing status updates to users, and most importantly, promoting responsible AI. The builder pattern is one of the most well-known design patterns in object-oriented programming. Even if you didn't know its name, it's likely that you've used it at some point without realizing it. This pattern is extremely useful for progressively building complex objects, providing great flexibility and control over the creation process. Thanks to this, we can generate different representations of the same object. It's worth noting that this pattern is used by Semantic Kernel to construct its kernel. Next, we will explore it with a simple and practical example. Imagine you want to create an application for designing pizzas. We know that there are numerous varieties that can differ based on the type of crust, sauce, and toppings. If we represented a pizza in a class diagram, we would likely have a pizza class with the properties toppings, sauce, and dough. In C#, the pizza class could look like this, with the properties we mentioned, toppings, sauce, and dough. In Python, the definition of the pizza class would maintain the same structure and fundamental properties. Now, we will define a class that includes methods for creating the pizza, among them setSauce, setDough, setToppings, and build. It is important to note that each method, except build, returns a reference to the same pizza builder. This allows you to chain calls to customize the pizza step by step. Here is the code in C#. Observe how an instance of the pizza type is maintained, which is modified each time you call one of the methods, for example, setSauce. Upon finishing the build method, it returns the final instance of pizza. Similarly, here is the implementation in Python. The logic is similar. A reference to a pizza is maintained, and it is modified as the methods of the class are invoked. Finally, the build method returns the created object. We could construct the object as shown, creating an instance of the pizza builder and calling the methods to set the properties. In the end, build gives us the fully configured instance. This flexibility allows you to skip methods if they are not needed and change the values freely. Here is the equivalent code in Python, following the same logic to create a pizza object. Let's look at an example of the builder pattern in action. This is a very simple example, but it will undoubtedly help you better understand how this pattern works and how Semantic Kernel uses it to create different instances of a kernel. Okay, you can see on the screen that we have a class in C#. This class is called pizza. And here are the different properties we mentioned in the slides. Finally, we have overridden the toString method to simplify return what the pizza is made of and how it is composed. Next, we have a class called Pizza Builder. You can see that as part of this class, we are defining a private field that belongs to the same class and is of the type of the final product we want to create, which is a pizza. So this representation of the pizza will be the final product we are creating as we invoke the different methods that are part of this class. Here we have the different methods such as setDough. You can see that here, for example, we are passing the description of the dough we want to use to build this pizza. You can see that this internal product is the product that is modified as these methods are invoked. You can see that here this property dough is assigned the parameter passed as part of the invocation of this method. Finally, it returns an instance of the same type, Pizza Builder. This is done with each of the methods. setSas, notice that it similarly assigns a value to the property sas, which is part of the pizza, and once again returns this Pizza Builder. The same happens with setToppings. Notice that this build method, which we have at the bottom, is the method that actually returns the finished product. This is the only way to access this pizza object because you can see that the pizza is actually a private instance. To get that reference with the already formed object with all the characteristics we have assigned as each of the methods is invoked, it is returned through a return. The build method is the one that will help us obtain the reference of the finalized object. Finally, you can see how what we have done, which returns a pizza builder, allows us to concatenate each of the methods, just as you can see in this example. You can see that a new pizza builder is created and each of the methods is invoked to form this final pizza. Each of the methods is invoked, although if you wanted to, you could skip one of them since it is not necessary to invoke all the methods. There may be a method that remains uninvoked because, for example, you might not want to add tomato sauce or something similar. You can do that without any problem. And finally, the build method is invoked, which is the one that actually returns the constructed object. So, when you use Semantic Kernel, you will see this pattern frequently. It's used to create that final object. You may have even seen it used in other programming languages or other technologies in .NET, where that type of object is formed. Finally, let's run the application so you can see what happens. You can see here how this pizza is composed through the different parameters we have assigned during the execution of each of the methods in the pizza builder. This is how the builder design pattern works. Remember that there are many ways to implement a design pattern. We are simply given the general guide on how we could implement it. So this is a representation of that design pattern. To carry out the demonstrations of how to create a kernel with Semantic Kernel, we will learn how to create an API key for both OpenAI and Azure OpenAI. Let's do this first for OpenAI. To achieve this goal, we need to head to the website platform.openai.com, which is the site you are currently seeing on your screen. It is important to note that you should have already created an account with OpenAI. It is also important to note that you need to deposit a certain balance to run different tests. In other words, so you can use the various services of OpenAI through the API. So once we are on this page, which is the default page, we will navigate to the section that says Dashboard. Once we are here, on the left side, you will see an item that says API Keys. Let's click on this option. You will see all the secret keys you have previously created, in case you have used this service before. If not, you need to click on this green button that says Create New Secret Key and give it a name, for example, SK Cars in my case. I will leave the project as default with all permissions and click on Create Secret Key. Why? So that a new key is created, which I can use through the different videos you will be watching. Once the key has been generated, we will click on this button that says Copy, as we will head to our machine where we are. We will save this API key information as an environment variable, so that we can easily and securely retrieve it later from Visual Studio. So once we are in Windows, we will type variables to bring up the option that says we can edit the environment variables for the account. Let's click on the button that says New. We'll paste the API key as the value of the variable, and I will name it skcars OpenAI key. This is to ensure that we can easily retrieve this API key from Visual Studio. Remember, if you plan to change this name, I recommend saving it somewhere where you can quickly reference what name you assigned to this variable for future use. I click on the button that says OK. We can see that the variable has been created. We click again, and with this, we have created an OpenAI API key to use from Visual Studio, and we have also correctly saved it as an environment variable. In this video, you will learn how to create an API key to connect to Azure OpenAI services. It is important that you have previously created an account with Microsoft Azure Services and fill out the form to request access to OpenAI services and have been approved to use these services. So once you have completed these prerequisites, you need to go to the Azure portal, which you can find at portal.azure.com. Next, we will click on this option to create a new resource. In the search box, we will enter Azure OpenAI to look for the Azure OpenAI service or services. Here it is. We select this option. We will indicate that we want to create a new service of this type. Select the subscription. We will create a new resource group. For example, skcars. Once we have entered this information, I will select a region, for example, Sweden Central. We will specify a name for this resource, for example, skcars. We will indicate what the level or pricing tier is. We select standard S0. Next. We select Next. Next. Finally, we click the button to create or initiate the creation of this resource. Once the deployment is complete, we click on this button to go to the resource. You can see that our resource has already been created. Once we are on the overview page of the resource we created, we will go to the section labeled Resource Management. We will go to the section that says Keys and Endpoint, because we want to save the location or region, or rather the endpoint, and also a key. Any of the keys will work correctly. I will proceed to copy the endpoint. I will go to my machine, once again, open the section to edit the environment variables, click on New, paste the environment variable, and name it, for example, skcars Azure region. This is to specify the region where our AI resource or resources are stored. I will click on the button that says OK, and again on OK. The next step we need to take is to also save the key. So I will go back to the Azure portal, copy one of the keys, return to my machine once more, open the editing of the environment variables, create a new variable, paste the key we just copied, and name this environment variable skcars Azure key. I will click on OK, and you can see that we now have this pair of environment variables created correctly. I will click on it, and with that, we are ready to start using Azure OpenAI services within Visual Studio. It's time to roll up our sleeves and create our project to start using OpenAI services. How do we do this? Well, let's head to Visual Studio and select a console app template since we are creating a simple application for various demonstrations. I will click on Next and name it, for example, SK Kernel. I will click on Next, will keep the pre-selected options and click on Create to create this project. I will delete all the pre-created code you might see on the screen. The next step to start using Semantic Kernel is to install the NuGet package that will enable this framework as part of the project. To do this, we go to the Solution Explorer, right-click on the project, Manage NuGet Packages, and search for Semantic Kernel. You can see that as part of the results, we have a large list of various plugins or different NuGet packages we could use. In our case, we are interested in this package, Microsoft.Semantic Kernel, which is the core package. We click on Install, which will start the installation process. We apply the changes, accept the licenses, and see that it's a fairly quick installation. Let's save the changes, close this section, and the next step we will take is to create the environment variables to obtain the various values we have pre-configured as environment variables. To do this, we will create a first variable named OpenAI key, which will be equal to environment.getEnvironmentVariable, and here we need to specify the name of our environment variable. In our case, remember that it is the term we had entered previously. Please ensure that this name matches the one you have or the one you previously saved in the environment variables. I will duplicate this line a couple of times and change only the variable names to Azure region and then to Azure key. I will change the term or this element that allows us to indicate which variable we want to obtain. In the second case, it is SK cars Azure region for the Azure region. In the third case, it is SK cars Azure key, which helps us identify the Azure key for the service. The next step is to create a builder, just like we did with the pizzas in the example on the slides. How do we do this? Well, we need to define that we want an object of type kernel. Notice that this namespace automatically gets added. We will indicate that this first kernel will be called OpenAI kernel. This will be equal to kernel dot, and we have a method called createBuilder that will allow us to essentially create a builder with all the specified characteristics. In our case, we are interested in using a method called @OpenAI chat completion, which will enable us to use the OpenAI service for this chat completion model. As you can see, the method is quite descriptive. We need to basically pre-configure this option or method with different parameters. What are those parameters? Well, you can see that we need to specify the model we want to use. We have other features that we could essentially complete. In case you want to know the possible values you could use for the model ID, you can refer to the official documentation, specifically at platform.openai.com/docs/models. Here you will find the list of different models, LLMs, or even other types of models that you could use as part of your applications. You can see that, for example, we have different aliases for each of the models. If you have heard of this model, GPT-4o Mini, you can see that it refers to the identifier displayed on the screen. So this identifier is what we will copy and paste as part of the configuration for this method, or rather, this instance of the OpenAI chat model. The next step is to place a comma and specify what the OpenAI client is. To do this, we will use a variable called OpenAI key, which is the key that will give us access to OpenAI services. Once we have configured this, remember, we will invoke a method called build, which will return the object configured with the characteristics we have specified, in this specific case, a model that allows us to complete text using the GPT-4o mini model. In the case of OpenAI, the same key can be used to access all services, so there is no need to carry out any additional configuration. Okay, this is the first configuration we have done. Now, if you want to connect to an Azure OpenAI service, what would you need to do? Well, we would have to create a new instance of a kernel. Since this is a kernel that will be configured differently, we will create a new instance called Azure Kernel, which is equal to, once again, using the kernel class, the createBuilder method. This time, we will not use the method we saw previously. Instead, we will use the add Azure OpenAI method, and the method is called add Azure OpenAI chat completion. We see that the name is very similar. The term Azure has simply been added to indicate that we are using an Azure service. Now, in this specific case of Azure, it requests some slightly different data than OpenAI. What are these data? Well, it requests a deployment name. It also asks for an Azure OpenAI client and other data that we could configure if we wanted to. You might be wondering at this moment what this deployment name is that we need. Well, in the case of Azure, we need to create this resource beforehand. How do we do this? We will go back to the Azure portal. Let's go to the Overview section. You can see that at the bottom, a button appears that will send us to the Azure AI Foundry portal. Let's click on this button. This opens a new window for us. This takes us to the chat playground, where we can basically create all the resources we need, as long as they are within the limits or quotas available to our account. We see many options. We are particularly interested in this option that says deployments. This section essentially allows you to configure the different deployments for the various resources you want to use, whether for chat completion, image generation, text-to-speech, etc. In our case, we will click on this option that says Deploy Model and indicate that we want to deploy a base model. You can see in this display the full set of different models available or that we could create. In our case, we are interested in creating a new instance or deployment of GPT-4o mini. That is the model we will select. We will click on Confirm to confirm that we want to create a resource of this type. Here we can carry out the customization of this deployment if we wish. We can select a different version of the model, and we can configure the token request limit per minute. Here we could increase it as much as we want. In my case, I will set it to, for example, 80,000 tokens per minute. We could also configure a content filter if we choose to. Let's leave this option on default and click the button that says Deploy. This essentially allows us to use the same key and region, while specifying a deployment name to carry out different invocations to the API. Now, I will copy this deployment name. I will return to Visual Studio, and I will paste the deployment name that I just created. Next, we can configure more options. In my case, I will set the Azure region by specifying the Azure region. I will place a comma because I also want to configure the Azure key. Finally, as I did before, I will invoke the build method to return this new object with the specified characteristics. With this, we would have two kernel-type objects that would help us invoke AI services for various operations, whether using the OpenAI service or the Azure OpenAI service. In this video, let's see how to use the chat completion service with the kernel we created earlier. How are we going to do this? Well, once we have created the instances of the kernels, we will define a new variable called prompt, which will be equal to, and here we will write what we want the LLM to return. For example, we can ask it to write a short poem about semantic kernel. Once we have created this variable, we will invoke the service that will allow us to get a response from the LLM. To do this, we will create a new variable called result, which will be equal to, here we can use either of the two kernels we created earlier. Let's start by testing the OpenAI kernel, which is the OpenAI service. We have a method called invoke prompt async, which will allow us to invoke the LLM in a very simple way. We will pass in the prompt that we want to use or send to the LLM. Notice that we don't have to do anything else. With this simple invocation of the method and the configuration of the prompt, we already have a service set up that allows us to send a prompt and receive a response. Finally, we will indicate console.writeLine and specify that we want to print the result with its result property. In just 3 lines of code, we will make an invocation to the service. Let's start the application execution to see what this returns. Okay, and you can see that after a few seconds, we have the poem about semantic kernel that has been generated by executing this method. Now, the next step is to understand how we could use the Azure OpenAI service. As I mentioned earlier, Semantic Kernel is a framework designed to make your life easier. To achieve this objective, all we need to do is use the kernel we want or change the kernel we want to use. Instead of using the OpenAI kernel, we will use the Azure OpenAI kernel. Note that we do not need to change anything else. All the remaining code is transparent, and we do not need to change anything since we are creating the same kernel or an instance of a kernel that executes the same methods. Therefore, the result would be the same. We'll run this application to see if this is true. Notice that we already have another response from a different LLM, or rather from a different service, returning this poem without having changed almost anything. All we did was essentially change the kernel we wanted to use, and the remaining code is the same. Now, in case you want to configure how the output result will be for the LLM, meaning that you can specify, for example, the maximum number of tokens, the temperature, etc., other parameters that you have likely seen when using OpenAI's Playground. Well, this is possible by creating a new instance of the OpenAI prompt execution settings type. How do we do this? I will create a new variable called options that is equal to new OpenAI prompt execution settings. As part of the parameters for this class, you can see that we have a lot of parameters that we can specify. For example, let's set the maximum number of tokens to 50 and the temperature to 0.9. From here, you can configure all the parameters you want to set up the response from the LLM. In my case, I will only assign this pair of properties. Next, we need to go to the invoke prompt async method that we used earlier. This is because you can see that a kernel arguments type is expected as the second parameter. Therefore, we are going to create a new instance of kernel arguments, and you can see that as part of this kernel arguments constructor, there is an overload that allows us to pass a prompt execution settings type. Rather, it's this one. Basically, this type is the same as the one we specified. That is to say, it relates to the type I showed you regarding OpenAI prompt execution settings. Thus, we can indicate that the parameter for kernel arguments is equal to options. Once we have done this, you can see that we no longer have any issues, because we are configuring the kernel arguments for this invocation to meet the options we previously specified. Let's see if this works correctly. Okay, and you can see that indeed this poem cuts off after 50 tokens, because that is a parameter we specified as part of the LLM response options. This is how you can better configure this LLM output to perform different settings according to your needs. So this is how we have configured both the OpenAI kernel and the Azure OpenAI kernel to return an output and also to configure that output. The chat completion service also allows us to stream the response. What does this mean? Well, it provides a response similar to what we see in the ChatGPT chat service. That is to say, we can see in real time how one of the texts is being completed. How can we implement this? As part of my solution or project, I'm going to create a region for this first demonstration that we have done. I will copy this code and comment it so that we have the different examples we are working on separated. Okay, so we have here the same code that we had previously. What I'm going to do this time is remove this line of invoke prompt async and also this console.write line, as we will be using a different approach. How do we do this? We will indicate a wait for each and in parentheses var chat update in OpenAI kernel, and we will use a different method than the one we had used before, that is invoke prompt streaming async. This time we will use a generic to indicate that we are expecting this type to be of the type streaming chat message content. Finally, as part of the parameters for this method, we will send what prompt we want to use. Basically, what we are doing here is indicating that for every update in the LLM service, for each completion that exists, we want to process that completion to display it to the user. So, as part of each for each, we will check if chat update, that is, if the update's content length is greater than 0, meaning if we actually have content as part of this output, and we will create a variable of type string called full message, which will initially be equal to string.empty. So when we have an update with a length or content, basically we will indicate full message plus equals chat update.content. That is, we will concatenate that response to show it to the user. Finally, console.write will print chat update so that the user has real-time feedback on the text being completed. So, to make a better test, instead of prompting to write or return a short poem, we will indicate to return a long poem. Let's test this application. We start the execution. You can see that in real time, we are observing how this poem is being completed because we are using this feature of chat completion streaming. Let's close this window. Now let's test using the Azure OpenAI service, changing the previously used term from OpenAI kernel to Azure kernel. We start the execution of the application. You can see that again we have the same behavior. However, we are now using the Azure OpenAI service. So this is how to perform chat completion streaming using Semantic Kernel. Once we have learned how to use the chat completion and chat completion streaming services, we will learn to generate images using DALL-E and Semantic Kernel. How do we do this? Well, let's first go to the section where we configure the kernels. What we need to do is first configure the OpenAI kernel. Performing this action is actually very straightforward. We simply need to add the image generation service as part of the kernel configuration. We will specify that we want to invoke a method called addOpenAI text to image. You can see various parameters that we could specify. We could specify the API key, the org ID, the model ID, etc. What interests us is to make this as simple as possible. So we will specify that we want to use OpenAI key. This is the key of the service we previously configured. Now, you may notice that this gives us an error message, but this is not related to what we just did in terms of a syntactical error. If you hover over this error message, you can see that we have an exception here indicating that this method is being used or has basically been defined experimentally for evaluation purposes and could be changed or even removed in a future package update. To remove this error message, we will hover over this tool icon that appears beneath the error. In the option that says Suppress or Configure Issues, we will select the option Suppress SKEXP0010 in the source code. Once we have this option selected, we press it or hit the Enter key. You can see that this removes the error, and we now see this Pragma warning disabled message that allows us to basically remove this error message as long as we have this file or source code open. I will cut this Pragma and position it at the top of the source code. I will remove these comments because I want any test we run to disable this restriction we saw earlier. So with this, we have already configured the method that will allow us to generate an image from text. Now, as part of the configuration, you can see that we also have a model ID that we could configure if we wanted to. You can see that the description indicates this is the model for image generation. If we return to the OpenAI documentation, you can see that we have the different models available to generate both chat and image components. We are particularly interested in the model called DAL-E, which is essentially the service that allows us to generate images from text. You can see that currently there are only two models, the DAL-E 3 model and the DAL-E 2 model, although it is possible that this list may expand in the future. By default, the DAL-E 3 model is used. So we do not need to configure anything, you just need to know this in case you want to use a different model in the future. For the configuration of the Azure OpenAI kernel, this changes a bit. I will go to the Azure OpenAI documentation, specifically to the list of models for the Azure OpenAI service. You can see here a list of all the models we could use within the Azure OpenAI service. Again, I will go to the section labeled DAL-E, and you can see the description of the models here. What we are actually interested in is this table, which indicates the summary of availability, both by region and by the types available. If we go to the table, we can see the list of all the available models that we can use. Remember that we are interested in knowing the availability of the image generation service. Rather, we will search for DAL-E. Okay, we have the availability here. You can see that we have the service, and here you need to ensure that the region you have selected or the region you want to use for image generation has this service available. In our case, we can see that the DAL-E 3 service is available, for instance, in Australia East. You can also see that it is available, for example, in the East US region, and other regions that you could use for this image generation service. In my case, Notice that I have created my resource in Sweden Central, so I can create images using the resource I previously created. So I will go to Azure OpenAI. I will again head to the Deployments section. I will indicate that I want to create or deploy a new base model. As part of this table, we will look for the model called DAL-E3. We confirm the data. We will leave the pre-selected or pre-created options and create this resource. After a few seconds, we see that the resource has been created successfully. We will copy the name we specified for the creation of this service. We return to the Azure OpenAI kernel configuration section. What we will do is, once we have invoked this method of add Azure OpenAI chat completion, indicate that we want to use the method add Azure OpenAI. We have here the method add Azure OpenAI text to image, where we need to specify the deployment name as the first parameter. We will indicate that the deployment name is equal to DAL-E3. However, in this specific case, we also need to configure the endpoint, as it is a very important or necessary piece of information to use the service. Fortunately, we have already stored this information in a variable called Azure region. Finally, we will specify the API key, which we have also saved in Azure key. This is how we configure the kernel to make it available for generating images using text. Now, once we have created this pair or configured the kernel to generate images from text, we need to modify the part that will allow us to generate images. How do we do this? Well, I will quickly create a new region. Once I have created this new region, the first step is to obtain the necessary service to generate the images. We will do this by defining the variable called, for example, service, which will be equal to OpenAI kernel. We are going to use the OpenAI kernel. And we need to invoke a method called getRequiredService. The service we are interested in will be specified through the interface iText-to-image service. We will place the closing parentheses and semicolon here. Now you can see that this generates a new error that is not related to the syntax, but rather indicates that this service is available only for evaluation purposes. Once again, to solve the problem, we will indicate that we want to suppress this error in the code. I will copy this pragma and paste it after this line that we previously pasted. I will remove these comments. With this, we are ready to generate images from text. How do we do this? Well, we will use the service by declaring a variable called generated-images, which will be equal to await using the image generation service through a method called getImageContentsAsync. Here, what we can do is essentially create a prompt that allows us to generate the image. We will quickly create a prompt named, for example, image prompt, which will be equal to beautiful sunset over the mountains. Let's proceed. We will pass this parameter, image prompt, as part of the parameter for executing this method. With this, we will finally do a console.writeLine passing generated images. We will indicate that we want to retrieve the first image that this service could return, .uri, if it is not empty, toString. What we are doing here will essentially allow us to obtain the URL of the generated image. Here I have an extra parenthesis. So with this, we could print the URL and see it in the browser. Now let's run the application. You can see that this correctly generates a URL for us. Let's click on the image. Okay, you can see that we already have this image generated through the image generation service. It is an image generated by DALL-E and the OpenAI service. Let's return to Visual Studio. We will change the OpenAI kernel to the Azure kernel. Let's run the application once again. You can see that we haven't changed anything else in the code. Let's start executing the code. After a few seconds, we can see that we have this URL generated by the Azure OpenAI service. Let's proceed to open this image. Okay, you can see this beautiful image generated by the DALL-E service. Now, in case you want to configure the options for image generation, you can do so through the OpenAI text-to-image execution settings class. How do we do this? Well, we will declare a new variable called options, for example, which equals new OpenAI text-to-image execution settings. You can see that as part of the configuration parameters of this class, we have properties such as specifying quality, size, style, among other options. How can we know the values we can assign for each of these parameters? If we examine the quality property, we would see that it is a string type property. Well, what we can do is go directly to the source code of this class. Here you can see that as part of the comments for each of the properties, we have the valid values that could be used for generating an image. For example, for quality, we could specify the values high, HD, or standard. We see that for the style part, we could specify vivid or natural. For example, let's copy this value of natural. For quality, we specify, for example, high. Let's also specify a size. We'll set the values, for example, to 1792. And as the second value, 124. We will also specify a style that is equal to, for example, vivid. Once we have configured the options for generation, we will indicate that execution settings equals options, where we have defined the characteristics for image generation. I will change these values so that it looks better, using a portrait size, so you can see that these values really modify this image. I will then start the application execution. After a few seconds, we have our new URL. Let's take a look. This is the image that has been generated. You can see that it has a portrait appearance due to the different properties or values we have assigned to the properties. So this is how we can create text images or use this image text service, configuring the options to have an output that is more in line with what we need. The next thing we will do is see how we can generate audio files using Semantic Kernel. To do this, we will first go to the kernel configuration section once again. This is necessary because we need to add the capability to use this text-to-audio generation service. So, as part of the OpenAI kernel, I will indicate that I want to use the method to add OpenAI text-to-audio, as you can see on the screen. Here you can see that in this specific service, you are asked for the model ID you want to use. Once again, let's return to the OpenAI documentation. You can see that as part of the different services, we have a service called TTS. This is the service that will allow us to convert text to speech. You can see that we have two models available, TTS1 and TTS1 HD. You can see the description of the various use cases for each of these models. So once we know which model we want to use, we will return to Visual Studio and specify the model name we will use in this case, which is TTS1 in my example. Next, we need to specify what the OpenAI API key is. We will indicate that this API key can be found in OpenAI key. With this, we have configured the OpenAI kernel. For Azure OpenAI, we again need to refer to the table that indicates where the different models are available. Let's search for the model we are interested in. These are the models. You can see that we have here the TTS and TTS HD models. They are the equivalents to the OpenAI service. If we look at the table, we see that it is only available in two regions. The first region is North Central US. The second region is Sweden Central. Therefore, the resource I created previously will also help me create this text-to-speech service. I will then return to Microsoft Azure. I will head back to the deployment section. I will indicate that I want to deploy a new base model. As part of this table or section, we see that we have the TTS and TTS HD instances here. So if you want to create one or the other, you must first create a deployment for each of the resources. In my case, I will create a deployment for the TTS service. I confirm the deployment and create the resource. Once this has been created, we will copy the name of the deployment, return to Visual Studio. This is because we want to use a new method as part of the kernel configuration for Azure OpenAI. So we add the invocation to the method add Azure OpenAI text to audio. Here it asks us for the deployment name, which will be the name we copied earlier. It also asks for an endpoint, which will be the same as Azure region, the variable that contains the Azure resource region. Lastly, we will specify the API key, which is again found in the variable called Azure key. By doing this, we have configured the Azure OpenAI service to generate audio files from text. The next step we need to take is to create or rather obtain the service that will allow us to generate those audio files. So here I have briefly created a new region for this demonstration. We will create a new variable called text-to-audio service, which will equal to, let's first try the service using the OpenAI kernel, meaning we invoke OpenAI kernel.getRequiredService, and we will specify that we want the service text-to-audio service, as we see on the screen. The next step is to define the content, that is, what text will be converted to speech. For this, I will create a new variable called content, for example, and I will copy and paste a text string that I have prepared in advance. This string can be anything you want. In my case, I have a pre-written string here. Once we have defined this string, we will proceed to configure the service to specify which voice we want to use, the response format, the speed, among other parameters that we can also configure. To do this, we will specify that we want an instance of type OpenAI text-to-audio execution settings. We will call this variable execution settings, which will equal a new instance of this type. As part of the configuration, you can see that we have various parameters that we can configure. We will specify that, for example, the voice will be equal to Alloy. We will indicate that, for instance, the response format will be equal to MP3. For example, the speed will be equal to 1.0, although you could change that as you wish. In case you want to know the different values you could use for these parameters, you can refer back to the OpenAI documentation. Here we have the TTS section, as I showed you earlier. If we click on this link, which allows us to know the voice options, you can see the different parameters that we could use. For example, for the voices, we could use Alloy, Echo, Fable, Onyx, Nova, Shimmer, among the currently available voices. Here we have the configuration of the output files, for example. Here you can basically find all the information you need to use this service correctly. Once we have specified the configuration options for the service, let's go ahead and generate the audio file. To do this, we'll create a variable called audio content that is equal to await text to audio service using the getAudioContentAsync method. As part of the parameters, note that it requests a text, which is the text variable we defined earlier. So let's pass the content. We also have the option to specify the options for executing this method. In my case, I called the variable execution settings, where I configured the different parameters. That's all we need to generate an audio file. Now, you may notice that as part of the response from this method, getAudioContent actually returns a task of type audioContent. Somehow, we need to save the result on our local machine to play it correctly for this demonstration. So, I will create a variable named path, which will be equal to, for example, the in the test folder. This is because this is the location I want to use for the generated files. Here I have an error, and I have already corrected it. The next step is to create a variable called, for example, audio file path, which should equal the combination using the path class. This will combine the base path we defined earlier, and we will name the resulting file audio.mp3. Although here you could implement some type of coding to assign a unique name to each audio file according to your needs. Finally, we will indicate await file.writeAllBytesAsync, which is this method. Here we will first pass the path where we want to save the audio file, which is audio file path. Next, we need to pass the byte array, which essentially contains the audio file or information. We can obtain this through audio content, which is the service response. We have a property called data, which we check is not empty. Then we have a property called value. And finally, we have a method called toArray to save this information to the specified path. Let's save all the changes and run the application. We'll simply display a console.writeLine to indicate that everything was executed correctly. Before running the application, I will add the pair of dots that I missed in the root path. Otherwise, I might encounter some issues. I start the application execution. After a few seconds, we see this message indicating that the file was created successfully. I will open this folder called test, where we already have the audio file named audio.mp3. I will play it so you can listen to it. This is the audio file generated from the string I provided. This is how we can generate audio files. I will change the kernel being used. I will go to this first line, and instead of using OpenAI kernel, I will specify Azure kernel, which is the service I want to use to create this audio file. Notice that everything else remains the same. There is no need to modify anything else. I'm going to delete this audio file. To show you that the file is generated again, I will start the application execution. After a few seconds, we see this completion message. Let's go back to the folder. Let's quickly run the file. This is how we can create audio files from a text string using Semantic Kernel. Now let's see how we can extract text from an audio file using Semantic Kernel. To do this, the first step is to define the path of the audio file. We will create a variable called, for example, audio by name, and we will copy the path we used in a previous video. The file is named audio.mp3. Once we have defined the audio file, we will go back to the kernel configuration section. This is because, first, for the kernel that uses OpenAI, we will add the use of the method add_OpenAI audio to text, which you can see on the screen. Once again, we are asked to specify the model ID. Therefore, let's return to the OpenAI documentation page and head to a section for the model called Whisper. Notice that we have all the information about this model, and it states that the available model is called Whisper 1. Thus, we will copy this model and paste it, as it is the model we will use to extract text from an audio file. Next, we will once again use the OpenAI API key. Remember, we have it stored in this variable OpenAI key. With this, we have already configured the OpenAI kernel. Now, in the Azure OpenAI kernel configuration section, we will use the method add_Azure OpenAI audio to text. Here, we are asked for a deployment name. So let's go to the Azure portal. We will indicate that we want to deploy a new base model. In this new window, we will select the model called Whisper, which will allow us to extract the text from the audio file. Note that we have some recommendations or restrictions indicating that the audio file must be smaller than 25 megabytes to use this service. This applies to both Azure OpenAI and OpenAI. We will indicate that we want to confirm the creation of this resource. I will click the button that says Deploy to carry out the deployment of this deployment. Once the deployment has been created, I will copy the deployment information, return to Visual Studio, and specify that this is the deployment we need or will use for the speech-to-text conversion. Next, I will specify the endpoint, which is available in Azure region, as well as the API key available in Azure Key. With this, we have configured the pair of kernels to perform this speech-to-text conversion. Once we have done this, we will return to the example region and obtain the service by creating a variable called audio to text, set to OpenAI kernel.getRequiredService, and we will indicate that we need an instance of the type iAudioToText service, which is the interface you can see on screen. Next, we will configure this service to determine, for example, the type of response, etc. To do this, we will state var execution settings equals new OpenAI audio to text execution settings, which is this class you can see on screen. And you can see that we have different properties that we can configure here. Let's configure the essentials or the basics. First, we will specify the language of the audio file. Let's indicate that the file is in English. We can also specify a prompt. This prompt will serve as an optional text that can guide the model's style or in some way continue from a previous audio segment. In my case, I will copy and paste a prompt that I have previously created. It's a very simple one. It says, "This is a prompt. You must respect the punctuation marks." We can also configure the response format to determine what output file we want to generate. If we want a text file, an SRT file, or a VTT file, by default, the generated response is JSON. We will use this format then. We could even configure a temperature to specify how random the generated text will be. Let's set it to, for example, 0.3 or this value of 0.3. Once we have specified the configuration options, the next step is to read the content from the audio file stream. So we will create a new variable named audio file stream equal to file.openRead to read the audio file located in audio file name. Next, we will create another variable called audio file binary data, which will be equal to await binary data.fromStreamAsync, passing the audio file stream that we have created previously. Finally, we will create an instance of the type audio content, which we will also call audio content equal to new. We will initialize this instance with audio file binary data, as it is one of the options to configure this audio content, that is, an array of bytes. Next, we will indicate that the MIME type is equal to null. With this, we now have the variable from which we extract the text. Finally, we will extract the content and display the result by creating a variable called textContent, which is equal to await audio to text service, and we will use the method called getTextContentAsync. We will pass parameters, firstly audio content, which is the variable we defined previously, and as a second parameter, execution settings, to inform the service how the generated response should be. Finally, we will indicate through a console.writeLine what the content is via textContent dot, and we have this text property, which will show us the result of the service call. With this setup, we will start the execution of the application. You can see that the response is quite simple. Here we have the text that has been extracted from the audio file we generated in a previous video. The next step is to demonstrate this by using, instead of OpenAI, the Azure OpenAI service, changing the kernel to Azure Kernel. Let's start the application again, and once more we have this text or content that has been extracted from the audio file. This is how we can extract text from an audio file using Semantic Kernel.